Hey, it's time to start up. I apologize for being a little bit late. Apparently, I have to now use two-factor authentication to sign into or start up any meetings. And I've not seen that before on my iPad, so it took an extra couple minutes to sort of do two-factor authentication for the iPad. So, but I'm here. How are y'all doing? Couple thumbs up, three thumbs up. Yay. Okay, so 4, 5. Is that like the new thing, the thumbs up icon? And do y'all know you can change the skin tone on your thumbs up? Oh, Ethan's not sure about that? Yeah, under reactions, you can somewhere you can adjust your skin tone. And I love that. So I'm just going to sort of start in by mentioning two email exchanges that I had, one of whom, like Matt, sort of said something to me last week, and I think I replied to him in a way that he was happy with over the weekend. He and I chatted a little bit, and he just got back to me just now, but I haven't fully read his email yet. But largely, he said, dude, would you make sure you have homework solutions there somewhere? And I said, okay, let's make sure we do that. And so I put in the Canvas a location where just the homework solutions along with the homework assignment will be found. And the first two homework solutions are there along with the first two homeworks. And then the third homework is there as well. When is that due? Some of you might wonder, how about Wednesday next? Not how about, I'm assigning it to be due Wednesday next week. So that way I can put the answers online Wednesday of next week. So that way you can make sure you have access to those answers as you're studying and getting ready for the exam, which is due by Friday of next week, Friday, November 6th. I guess we're heading towards November pretty quickly. But what I want to do is to mention the way that we'll do the exams next week. Wednesday, during the normal class session time from noon till 1 on Wednesday, I will, in theory, be in a meeting in Long Beach at the chancellor's office, and what that means is, well, we have lunch break. Usually, it's almost exactly noon till 1. I'll log into the class web site, not the class website, the classroom, what we're here now in, and I will. If you want to take the test Wednesday during the course of that noon to 1 time slot, and I'm not encouraging or discouraging, I'm just saying Wednesday from noon till 1, I will be able to put you in a Zoom room and during a breakout room by yourself. And during the course of the exam, if you got questions, you flag me, I go into your room and answer your clarifying question. I can rephrase a problem if that's going to be helpful for you. I'd like to do that. If you'd rather take the test at some other time, that's fine too. My Tuesday, Thursday, noon till 1 class, which is Stat 513, they're also taking an exam that day, the 5th of November. And between noon and 1, you're welcome to join that classroom, but to take your test in their classroom. Same deal. Everyone will be put into a breakout room individually. Anyone who's there from that class, plus any of you who would like to be there with me, able to clarify questions for you during the course of your exam, that's great. Those are the 2 time slots when I will be available for answering questions right while you're taking the test. Noon to 1 on a Wednesday, and noon to 1 on Thursday. And just for your information, I'm inviting them to also show up noon to 1 on Wednesday if they'd prefer to take their test a little bit early. But the exam will be due by Friday at noon. Actually, hold on. Okay, so I'll do one more time, but I haven't officially updated the Canvas yet. I will also try to have a Friday noon to 1 time slot as well, again, for clarifying questions. Again, that's during lunch break of the meeting that I'm going to be in. And so at least for part of the time, we'll be on lunch break. And because that, I'll be able to make that time slot available to you as well. And I'll bump back when the test is due to have it finished up by 1:15 on Friday for you guys. And so if you want to wait until that Friday time slot to take the exam, that's fine too. But that's the status. Is I would like to, in theory, have you all take the test early, rather than later. And week from today is actually about the last day that I want to tackle Q&A for homework and stuff like that, sample exam questions to get you ready for the test later in the week. And then you'll go away and study for a period of time and do well on the test. Okay, Sophia also emailed me, but I haven't replied to her email yet, but she confirmed what I have as a suspicion that, and Matt also mentioned this as well, that you guys don't have access to your homework grades at this point in time. And if you're wanting to know how well you've done on the lab activities, if you turn them in and they're not blank, you pretty much got full credit for doing the labs. And there's a fair amount of points for those learning activities. The homework sets themselves, I've emailed the grader about 3 times now, and I have not gotten a reply back yet. And COVID makes it harder for me to track him down. He's not going to be in the stat lab. So because that, what I'm going to be doing is coming up with plan B, which will probably involve me giving you about 50% of the points just for having done the homework. And then I'll be, the answers are online already, and then I will be grading them, but I won't have the ability to grade them super quickly. So certainly you won't have those graded before you're fully graded before your next exam. Certainly the first problem set is the lowest priority. The second homework set, I will start in on that one because that's most closely related to the material on your upcoming exam. And then Q&A in class is the best we can do right now. but I'm going to talk to the grader one more time. And if I don't hear back from him that, yes, I'm on it, and with a promise of here's when I'll get it done, I'm going to just sort of say, okay, well, we're not going to go with this scheme anymore, and I'll figure out something else, which will probably involve me grading. But that's not what I most want to do. I'm hoping this guy will pick up from where he left off. But certainly him not replying to me does suggest that maybe the issue is that he hasn't graded yet. But if it is an issue that he has and just it's a technical issue on my end, I can find it and fix it now that I've been informed how to do it. It might involve, again, me regrading all the problems, but if that has to happen, that has to happen. So that's administratively things I want to mention. Do any of you have administrative questions at all? I'm not seeing any administrative questions. If you do, certainly emailing is not a bad way to get hold of me to get those questions addressed. Oh, something in the chat. Okay, so yeah, there will be a link in the Canvas today for the R code is there as well. But yes, certainly I should update the link, and right as I'm finished up with the lecture portion today, what I will do is I'll update the Canvas links in the lab for today, so that way y'all can tackle the lab properly. And I want to mention that that will probably take about 2-3 minutes for me to update the links, and so that's a natural break time. Let's go ahead and plan on that. Any subject matter questions? Okay, so I'm gonna start in then by sharing a screen on from the iPad, a whiteboard, if you will, and then we'll do what we've done recently. Then we'll switch over to looking at the ACF and PACF within the context of R for these seasonal ARIMA models, or SARIMA, SARIMA models. Okay. And there's two standard notations, and you got to pick one or the other. Here's the notation I'm going to go with from here on out for the rest of the term. Capital P, capital D, capital Q. S would be the length of the seasonality. Lowercase p, lowercase d, lowercase q. Okay. If I say a process is seasonal ARIMA, you're sort of thinking, okay, it's ARIMA, but it's also seasonal. You're already familiar with lowercase p, d, and q. Okay. Literally, d is the number of first differences. And that really has the impact of 1 minus b to the power d, or upside down delta to the power d, multiplied by yt. Okay, so you're going to apply that number of first differences to your series. Lowercase p corresponds to our capital phi function. Phi of b is equal to 1 minus b phi 1 b minus phi 2 b squared minus dot 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 minus phi p b to the pth power. And then our third term q is going to correspond to our capital theta function b, which is 1 minus lowercase theta b1, theta 1 b minus theta 2 b squared minus dot 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 all the way up to theta q b to the power q. Okay, so that looks really familiar, and you're sort of thinking D has something to do with whether you have a trend or not. If you had a trend, your value for D might be 1. If you had a trend which was flat and then it curved up and it looks almost quadratic, you might go with a D of 2. Rarely do I see a lowercase d more than 2 in size. Okay. Usually we choose P and Q, lowercase p and lowercase q, to fit the data via BIC. We find that the best fitting models tend to be either with just autoregression, there's a P, but Q is 0, or just moving average, a Q being 3, 4, 5, and a P of 0, or P plus Q together, added up, if you will, less than a 5 or so. You might have ARIMA 312, or 411, or 510. Okay, all could fit reasonably well. BIC is probably the best way to select a model. What about these other terms, capital D, and I'm going to go with blue here for the seasonality. And we need to keep track of S, the length of the season, in capital D. What we have here is 1 minus B to the S, then to the capital D power. Again, that's a seasonal difference. B to the 12, if S were 12, that says, yeah, YT minus 12. And we're going to do capital D seasonal differences. So if you see in your data seasonality, your capital D should be at least a 1. If your capital D was 1, it should eliminate most of the seasonal pattern in the data. Sometimes I've seen a capital D of 2. Between lowercase and capital D, I rarely see the sum, lowercase d plus capital D, equaling more than 3. Sometimes I've seen a 3, rarely would be more than a 3. Okay. Capital P and capital Q, let's talk about capital Q, or capital Q is the order of the seasonal moving averageness, and I'm going to call that capital theta S for seasonal B, and that's equal to 1 minus capital theta S1 B to the S power minus capital theta S2 B to the 2S power minus all the way up to capital theta S capital Q, okay, B to the capital Q times S, the seasonal moving average. And so what you're looking here is maybe there's 1 or 2 capital thetas. And similarly, there's a capital phi S of B portion. And that's 1 minus capital phi S1 B to the S minus capital phi S2 B to the 2S minus all the way up to capital phi SP B to the P times S power. So in this context, I want to now write our model. So these are all the parts of the model separately. And I'm reminded again of that high school physics class where you did one whole page of calculations just to turn the page and take a few of the things you wrote down on the first page and put them into another long equation on that next page. So here's that next page. The SARIMA, capital P, capital D, capital Q. And I'm going to write this now in terms of 12 as though you have 12 data points per year, okay? P, D, Q, capital, or 12 is better than S for the length of the seasonality, but I wanted to write it out in its general form at least once. The model itself really looks like, as always, something times YT, okay, equals something times epsilon T. So YT, well, there's the seasonal and the regular differencing. 1 minus B to the power D, that's the regular differencing. 1 minus B to the 12th to the capital D power, that's the seasonal differencing. And now all I have to do is to put in the moving averageness and then the autoregression. Let's go with the moving average over here on the right. That's capital theta S of B. That's the seasonal moving averageness times capital theta of B times epsilon T equals capital phi S of B times capital phi of B. Okay, so those are the seasonality terms. We see seasonal differencing, seasonal autoregression, and seasonal moving average. There are also non-seasonal terms, just regular autoregression, regular moving average, regular differencing. Okay, so there we go. And then finally that regular moving average term there. And so it's basically saying you got something that's seasonal and something that's non-seasonal in terms of its autoregression and moving average structure. Now this is a model, and it's a false model. All models are false, but some are really pretty stinking useful. This is one of those, and you're going to find that even though you probably don't fully believe that real life things are in fact seasonally moving average, if a seasonal moving average pattern matches perfectly the nature of your autocorrelation structure, you could use it for short-term forecasts out 1 or 2 seasons quite effectively. So I guess what we need to do is to consider how to identify the sort of model we'd want to potentially fit, and that's going to be with the ACF and PACF, autocorrelation and partial autocorrelation function. And then we need to learn how to fit or estimate the parameters that are seasonal and regular. And then I guess deriving our prediction intervals and that sort of thing is good. There's one loose wrinkle that I'd like to sort of iron out before we move forward into talking about how to use the ACF and PACF to identify the nature of the best model. And that wrinkle is what happens if you were to say multiply something like that together. Yeah, literally, if I have Surima 1 0 0 12 1 0 0, it's just autoregression, but in 2 ways: regular autoregression, regular, and seasonal autoregression. On the left-hand side, we would have 1 minus capital phi S B to the 12th power times 1 minus lowercase phi B times YT equals then epsilon T. I could FOIL that thing out on the left. So what we have is 1 minus phi B minus capital phi S B to the 12th plus lowercase phi capital phi B to the 13th now times YT is epsilon T. This is almost like an autoregressive model of order 13 where phi2, phi 3, 4, 5, 6, 7, 8, 9, 10, 11 are all zeroed out. Only phi 1 matters, and the first seasonal phi matters because the 13th term here is a product of phi 1 and capital phi 1. So if I were looking at the partial autocorrelation function, I would see at lag 13 something happening. At lag 12, something should be happening. At a lag of 1, something should be happening in the partial ACF. But I will not see any action in the partial autocorrelation function from this model past a lag of 13. Let's talk about this wrinkle, but in the moving average sense as well. So if it's Sarima, 0, 0, 1, 12, 0, 0, 1, okay? My model looks like YT equals capital theta of B, capital theta 1, sorry, capital theta S for seasonal, times B, polynomial function of B, times capital theta regular B, epsilon T. And what we have here is 1 minus capital theta B, or I'm sorry, capital theta S, erase S, times B to the 12th, times 1 minus lowercase theta B itself, epsilon T. And again, let's do a little bit of work here and multiply those two left-hand terms together. What we have is 1 minus lowercase theta b minus lowercase or capital theta s b to the 12th plus lowercase theta capital theta b to the 13th power times epsilon t. So this is a 13th order moving average. Our 13th order moving average, where all of the terms theta 2, theta 3, 4, 5, 6, 7, 8, 9, 10, 11 are all zeroed out. Theta 12, the theta attached to b to the 12th power, at theta 1, those are fixed, and theta 13 is a product of the two of those. The term that would normally go out in front of b to the 13th power is completely determined by the parameter out in side of b, out in front of b by itself, and out in front of b to the 12th power. Okay? So if this was strictly moving average, I should see in the ACF at a lag of 13, something would be happening. At a lag of 12, something should be happening. Heck, at a lag of 1, something should be happening. My claim is perhaps even at a lag of 14, something will be happening. We could derive that, and perhaps that's one of the homework exercises, is to work on this sort of a thing and come up with a derivation of the ACF of this sort of a model. Okay, so let's switch gears and sort of go right into looking at data and what those data are like. And I'm going to, for the purpose of investigating the process, the seasonal moving average process, the seasonal autoregressive process, seasonally mixed models, Sarima models, if you will, I've written some code, and it's much like what you're going to be doing on the lab for the sake of looking at the ACF and PACF patterns that correspond to seasonality. Okay, so I'm going to share this desktop with you where I've got R running. And what I see here is, well, first off, a need to not apologize, but to note that R itself, remember how we use this arima.sim function for the sake of simulating an ARIMA model? You cannot do seasonal ARIMA sim. You cannot do a seasonal ARIMA sim, unfortunately. So what we're left with is rolling our own, and that's not too hard to do. So that's the nature of what we pulled off here. So walking you through the concepts and the code, I want 1,000 data points from a simulated series. I'm going to generate 1,100. Why 1,100? We'll talk about that in a little bit, but 1,100 epsilons are generated. My values for Y, I'm going to assign 1,100 of them to be missing, and shoot, the first 50 I'm just going to call zeros. So the first 50 Y values will be 0. If I want seasonal ARIMA 110, I need two parameters: seasonal autoregressive 1 and a regular autoregression of order 1. So I got a capital phi 1. The seasonality corresponds with the capital. A non-seasonality corresponds with the lowercase here. And yeah, the length of our season is 12. So all I have to do is to step my way through the data, and starting with the 51st data point, because the first 50 of them all take zeros. The 51st one will take capital phi times 12 time periods ago's Y, plus phi 1 times yesterday's Y, plus then epsilon for today. Okay, so Y today is phi 1 times Y 12 time periods ago, plus lowercase phi 1 times yesterday's Y, plus epsilon for today. And I'm going to step through the whole of the data that I'm creating that way. So I'm basically doing that ARIMA simulation. Now I started with a 50 values that are all zeros, okay? I'm going to start at the 51st and go through with the 1,100th. I'm going to call the first 50 or so the initialized, the next 50 the burn-in period. Okay, the 52nd data point, you know, it's going to be based on just the 51st, and that's it. The first 50s are all 0, so the 52nd data point will depend on Y the 40th, but that was by definition 0. Okay, so I'm going to sort of burn in over a period of 50 time periods my simulation. By the time I get to the 100th, though, I should be okay. And I'm going to peel off just the 101st to the 1,100th. I'm being left with exactly n data values. Then I'm going to plot the series itself and the ACF and the PACF. So let's see what patterns we see if I were to run all that. Okay, so here is my series upstairs itself, just by itself, the series. And just to make sure we can see everything nicely, I'm going to perhaps change that to a 2, 1, and hashtag that out. Now, when I call that hashtag that out, that's what I'm saying these days. I used to say £, or comment that out. Do y'all know what I mean, though? Use that character to make sure that that code is not run. So let's go ahead and plot the ACF and the PACF. And I'm spotting here, like I suggested, okay, at a lag of 10, 11, and 12, I spotted values in the partial autocorrelation function. My model that's seasonally and regularly autoregressive says at a lag of 1, yeah, you got a spike. At a lag of 12, you've got a spike as well. Turns out we have at a lag of 11, we got a spike. At a lag of 1, 2, 3, it seems as though we've got this little decay down from our regular autoregression. So if I had an AR model with a phi of 0.3, it's going to be quickly decaying, like it does here, from 1 to about 0.3 to 0.3 squared, 0.09. Yeah, that's quick decay. And then also at a lag of 12, I've got that term that we have corresponding to our seasonal autoregression. Now, if I looked here at just the peaks at a lag of 0, 12, 24, 36, I see almost a slow decay at the seasonal patterns. Again, this capital phi is applying to things that are 12 months ago. But 12 months ago depended on 12 months before that. So 24 months ago, there should be a correlation. And 24 months ago depended on 12 months before that. So at a lag of 36, there should be some autocorrelation. But I'm also seeing, like we suggested, at a lag of 13 and maybe 14, and shoot, even a reflection at a lag of 11, we see a pattern of decay and decay from the spike at lags of 12, 24, and 36, decay above the 36. So I'm looking here, I see seasonal autoregression, 1, 2, 3. Yeah, at lags of 1, 2, and 3 years, we see a pattern. And regular autoregression, that decay reflected there and there and there as well. The regular autoregression is in the partial autocorrelation function at a lag of 1, the seasonal autoregression at a lag of 12. So I look at this, I say Surima 1, 0, 0, 12, 1, 0, 0. And you knew that because you constructed the code. Well, that was easy. What about something that's seasonally autoregressive, but moving average in terms of its regular process? Again, the same sort of thing. Let's just jump right down to, well, the part of the model where I deal with the moving average. I subtract out theta times yesterday's epsilon, and theta in this case is a 0.6 positive. Phi 1 is 0.6 positive. Looking at those values, and maybe again, well, let's just look at the series as a whole. Let's generate that and look at the series itself. And it's hard to tell whether that's seasonal. If I blew it up, if I expanded out the x-axis so it's longer, more time periods, if I showed you just 12 or 24 or 36 months at a time, you might see the seasonal pattern sort of repeating over and over again. Okay? But let's look at just the ACF and the PACF after that, from that simulation. Okay, so this is seasonally autoregressive. So I'd expect in the ACF right there at a lag of 1, 12, 24, 36, I'd see that decay at seasonal periods. And seasonal autoregression says at a lag of 12, I should see a positive value in the partial autocorrelation coefficient. Seasonally autoregressive, but regular moving average, well, I should have some characteristics of a regular moving average in my model as well. At a lag of 1, the negative of theta is the ACF value. Okay, not exactly the negative theta, but the negative of theta standardized by some denominator term. And if theta was positive, like it is here, theta is 0.6, I'd see negative values, but decay towards 0 in the partial autocorrelation function. Okay. Well, those negative values that are decaying, okay, they're going to be reflected positive upstairs, and then at 24, perhaps negative if we even had a spike at 24. This positive, this negative here is going to be multiplied by the negative, or the positive value capital phi, there and there, there and there, there and there. So there are some standard patterns that in the lab today you'll explore for the purpose of identifying an approximate guess of the model that might fit. Once you have an approximate guess of the best fitting model, you estimate the model parameters, you check BIC, you look at the residuals to see if there are any departures from white noise. If the ACF says, you are missing spikes at seasonal periods, you need to adjust the seasonality in your model. If you see spikes decaying, okay, it suggests there's something going on that you missed with your fitted model. So I'm going to sort of start in on that pattern by looking at the spirits data like we've done before and start fresh. Here are the spirits data. I see seasonality. I see a trend. I'm going to do a seasonal difference. Spirits.d12 is the seasonal difference of the spirits data set, and I'm going to plot that itself. And you're spotting, perhaps if you look carefully, the bulk of these values are slightly below 0. If I drew a line in that's horizontal at a height of 0, so AB line, H equals 0, color. Well, let's just go with a color. Let's just go with, what color do you like? Dodger blue. I figure it's that time of the year. We should admit that some of you like the Dodgers. Is it clear that these are negative on average? Ryan says yes. Okay, so because they're negative on average, I'm going to need to fit a mean. Okay, if I include a mean, great. If I don't include a mean, there will be a problem in my estimates because it will cause, whether it's autoregressive or moving average, it will cause things to have to shrink back towards 0 when clearly we should be fitting something that's negative. The way you could deal with the non-zero nature of our series is you could take either a regular difference or fit a mean to the seasonal difference data. Okay, so your seasonally difference data, you could do a regular difference on top of that, which will cause the whole trend to be higher, or you could fit a mean to the first or the seasonally difference data. Well, let's just go ahead and look at the ACF and PACF of our seasonally difference data. And here's the ACF upstairs. Hard to see at lags of 12, 24, 36. So I drew in just right near 12, 24, and 36, those values. And if I was blowing that up and looking carefully, I'm going to spot here. Hold on. Are you still looking at my window? Same window as before? Or did I? Oh, shoot, I moved it off the desktop. I'm sorry. Darn it. Okay, so when I stare up close, I can see right at 12, a spike. At 24, a spike in the ACF. I don't really see it 36 or 48 or 60, a spike in the ACF. Maybe it's 60, but you know, that's hard to really see. But certainly 12 and 24, I see something there. And at 13 also. What about the partial autocorrelation function? The partial autocorrelation function, again, having to stare carefully, maybe I should move the salmon color line over a little bit further, but I see at a lag of 12 and 13 and 24, I see something's happening here. Okay, so let's think. 2 spikes at seasonal lags of 12 and 24, and then 36, almost, and 48, almost, and 60, well, probably not, but it's fair to say at 48, it's getting towards the outside of this region of zeroness. At 36, it's large for the typical spike. So it's almost as though I could say 12, 24, 36, and 48 is where I see some spikes. In the ACF, at lags of 1 year and 2 years, 1 and 2 seasons, I see something in the ACF I'm thinking seasonally moving average, because I see 2 spikes here, and then it cuts to 0. And this reflection term right near 13 and right there at 13 as well suggests to me that perhaps I should fit a model that's seasonally different, moving average 2, but autoregressive first order. Okay, let me say that one more time. Why I would jump right out and fit that. Again, 1, 2 spikes in the ACF at seasonal legs. So I'll say seasonally MA2. MA2 decays slowly in the partial. And we see here, if it was at lags of 12, 24, 36, and 48, it does seem as though spike, smaller, smaller, and then even smaller than that. I'm saying decay. I see decay in the partial autocorrelation function at integer multiples of 12. What's jumping out at me is moving average 2 is the seasonal nature of the model. And regular AR1 on top of that, again, because the reflection here and here. I see almost a reflection there. I don't know. It's really hard to justify, but yeah, at 23 and 11 and 13, maybe there's some autoregression of the first order as well. It's harder to see, but I can see hints of it. In honesty, what I did is I tried the model that was strictly seasonal MA2, and then discovered the residuals had some strong autoregression in them. So I added the AR2 or the AR1 term. So here's how I'd fit the model. And I like to remind myself in the name of my fitted object what exactly I was fitting. So it's a fit of a model to the spirits data set. And the fit that I've got is 0, 1, 2. So a seasonal difference where the seasonality is of length 12. And then seasonal second order moving average, but in a regular sense, a first order autoregression. So the code says, yeah, just say ARIMA, your data values themselves. Then you say the order of the model, the regular order 1, 0, 0. And then the seasonality components are next. The seasonal components, I say seasonal equals, well, shoot, like the model contains maybe a list. My list has the order of the seasonal components. The seasonal difference is MA2 in a seasonal sense, and the seasonality is of period 12. And I definitely wanted to include a mean. So let's go ahead and look and see what we get if we were to estimate those model terms. And maybe downstairs, I can look at the estimates reasonably well. Okay, so I see my AR1 lowercase phi1 is 0.45 with a standard error of 0.14. Significant. Well, the first order moving average that's seasonal, SMA for seasonal moving average, not significant. Okay, again, the estimate divided through by the standard error is a z-score. In the case of the seasonal moving average at length 2 seasons, if you will, I've got 2.27 with a standard error of 0.13. That's a z value of just over 2. It is statistically significant. Okay, just a quick note before sort of showing you the next part of this. If you have seasonal moving average at a length of 2 that is significant, you probably want to include the seasonal moving average of the first order. Most software packages don't allow you to easily just drop capital theta 1, but keep capital theta 2. There are some packages that do allow you to do that for the sake of model parsimony, but typically that's not something that's built into most functions. So I've got at least two statistically significant parameters. I've got an AIC value, but I want the BIC value. Boom. My BIC value, 2143 or 2144. Well, what if my model wasn't good enough? If I explore the residuals, if I look at the Young box stat for the residuals, I might very well say, you know what, there's a problem. I don't yet have all everything perfect. I might need an additional parameter to be estimated, maybe seasonal autoregressive order, sort of moving average of order 3. I could fit in a 0, 1, 3, 12, 0, 1, 0, 0. So it's just changing the nature of the moving average seasonal component. And if I were to go ahead and run that, you can see from BIC being 2147, it's higher, not as good of a model. In fact, that seasonal moving average, that capital theta 3 term, not statistically significant. It does help us pick up on the statistical significance of capital theta 2, but capital theta 3 by itself is not statistically significant, and BIC goes up from adding this extra model term. I don't love the model. I want to stick with the first one that I fit. Okay, so here's about the time when we're going to break and go into the lab. Again, give me 5 minutes after Q&A to make sure that everything is uploaded correctly on the lab. Okay, Gene mentioned that I've got our code there only rather than the lab file itself. And then I also want to put up this file, the one that I'm working on as well, because that might be helpful for you to key off of. There's enough built into the lab 10 portion for y'all, but in the lab code, but I want you to sort of have access to the example as well. So any questions on anything before I start poking away at that? Yeah, Rocco. No? You appeared. I figured you might have a question.
I have a quick question. If
Yeah. What's the
Rocco
question?
doesn't go. Instead of including this mean equals true,
Yeah.
argument, if you put in a 1 for your D
Yeah.
in the order part, would the model behave similar?
Great question. Let's try it. Okay. So instead of, I'll do a cut and paste of our earlier friend. My claim is the estimate should be comparable in many ways. Okay. But we'll actually see. Okay, so 1, 1, 1, 1, 0, and that should be a false, which is the default. Okay, so let's change that to a 1, and that one also to a 1. Okay, so clearly 2146 compared to 2122, BIC is lower. Okay, but one thing you might want to be aware of is the following. Because you are doing a regular difference, all of a sudden your series is one time period shorter. You have one less data point. And so that's going to cause your AIC values to strictly not be comparable between the two models. Whenever differencing changes from one model to another, AIC and BIC cannot be used for comparing between two models with different natures of differencing. Okay. What could we compare though? Well, let's look at sigma squared. Now, sigma squared, I have 22.79818. Earlier we had 28.18.743. It looks as though it's a little bit better, 22 rather than 28. So I might prefer this one, okay? And certainly the seasonal AR, I'm sorry, the regular AR1 is highly statistically significant, and seasonal moving average significant, and the second seasonal moving average also significant. So you could fit a mean. You could also do a regular difference. The regular difference is the more common pattern than including a mean. Both should be ways of dealing with a non-zero value for the series as a whole. One might be better than the other. Certainly in this case, because of the additional differencing, we're also fitting one fewer parameter. The mean we don't need to estimate. So we're good there. So do you want to ask a follow-up on that, Rocco? Or anyone for that matter?
Could you talk about what like fitting the mean is again, like why we're doing it and what exactly it's actually doing, like math-wise?
Well, if you have a non-zero mean in your series as a whole, if the mean was like negative 2000, then you should include a mean term, and it's going to estimate the mean and then subtract out that mu hat, if you will, from y before fitting an ARMA PQ or a SARIMA PDQ to the model. So a non-zero average says include a mean or do an additional differencing.
Am I like forgetting something? Like I don't remember like the average being non-zero being a problem.
Well, the way we dealt with it is we said just estimate the average with y bar and subtract out y bar before you go. Or you could include the mean with the include.mean equals true argument. We typically haven't done that, but that's a valid way of tackling a problem where there is a mean. Just as valid, taking a first difference of a series with a constant mean should then cause the first difference of that series with the constant mean to equal 0 on average. Differencing is helpful sometimes. You want to follow up on that at all, William?
No, I'm good.
Okay. So let's take our 5-minute break now, and then I will make sure that I get those 2 files uploaded properly. And thank you for letting me know that they were not uploaded in the perfect way before y'all dive in on the lab, because that would suck to not have access to the lab itself. Now, I think I had uploaded something, and those of you who are looking at it now under the assignments, do you see under lab 10, it's called lab 10 seasonal ARIMA. I see 1, 2, 3 things. The seasonal ARIMA spirits.r. Oh yeah, okay, got it. The thing that is yeah, that's what I need to change. Okay, so I'm going to delete that and put in the Word file instead. Thank you. It'll take me less than 5 minutes. If you want to just hang, that's fine too. But in 5 minutes is when I'll assign you into the rooms. Files. Okay. Boom. Okay, let me just check. Yeah, it looks as though it's a doc now. Can one of you verify if you're still here that you see a doc file when you hit reload? Got it. Okay, so I'm going to sort of open up some, I guess I'm going to stop recording and then I'm going to open up the breakout rooms.